This statement is not provable. This single statement G made Gödel's incompleteness theorem possible. It revealed that some true statements can never be proved. But Gödel developed the statement G based on two paradoxes. The second one is more fundamental, but far less well-known.
The first was the liar paradox. This statement is false. If it's true, then it is false, because that's exactly what the sentence says. If it's false, then it is true, because what it says is actually true. Either way, you end up with a contradiction. The liar paradox revealed that self-reference could produce extraordinary results. Gödel wondered whether the same idea could exist inside mathematics. But there was a problem. The liar paradox wasn't mathematics. It was written in ordinary language. Gödel needed a way to create a self-referential statement entirely within mathematics. That was the challenge. Then another paradox offered an intriguing clue, one even closer to Gödel's Incompleteness Theorem. Richard's paradox. Gödel even mentioned it in his famous paper. Imagine a list containing the decimal expansions of every real number that can be defined using language. Pi, the square root of 2, 1/7. Now suppose the list is complete. Every real number that can be defined using language is already on it. Now here's the twist. Take the first decimal digit of the first number and replace it with the next digit. Do the same for the second decimal digit of the second number, then the third decimal digit of the third number. And keep going forever. This creates a new real number. It differs from the first number in the first decimal place. It differs from the second number in the second decimal place. It differs from every number on the list in at least one decimal place. So it cannot already be on the list. And yet we can describe that new real number using a single sentence. The real number formed by changing each diagonal digit to the next digit. So this number can also be defined using language. It should already be on the list. Yet it isn't. That's Richard's paradox. It suggested that objects defined in ordinary language could be represented and manipulated through numbers. And once they were, those descriptions could even refer to an entire collection. The description itself became part of what it described. So Gödel wondered, if mathematical statements could also be represented by numbers, could mathematics describe itself? Not a statement about truth, not a statement about language, a statement about provability. Somehow, Gödel found a way to do exactly that. The result was a mathematical statement that says, this statement is not provable. This is now known as Gödel's statement G. It is a true statement that cannot be proved. At first, statement G looks a lot like the liar paradox. But there's one crucial difference. The liar paradox is written in ordinary language. Gödel's statement G is written entirely in arithmetic. Unlike the liar paradox, Gödel's statement G is a genuine mathematical statement. The liar paradox showed Gödel what kind of statement he needed. Richard's paradox suggested that self-reference might be recreated inside mathematics. Gödel made mathematics capable of talking about itself. How was that even possible? That's the story of the next video. Thank you for watching.